Good morning. My name is Ameya, and I'm going to be talking about my team's work on detection of environment transitions in time series data for responsive science. The upcoming Europa Clipper mission aims to study one of Jupiter's most fascinating moons, Europa. One of the instruments on Europa Clipper is PIMS, the plasma instrument for magnetic sounding. PIMS will study the properties of the plasma around Europa and Jupiter, especially its interactions with Jupiter's magnetic field. PIMS counts the number of charged particles within ranges of energies. Each range of energies is called a bin. PIMS operates in four different modes, with different sampling rates and energy ranges or bin definitions. Each mode is optimized for the anticipated plasma conditions in its region. The current mode switching logic is pre-scripted based on estimates of where regions lie and how far Clipper is from Europa. We raised the question, can we instead have a more adaptive instrument, one that can detect transitions between regions and switch modes automatically? We formalized this as a multidimensional time series problem. Here is an observation from the CAP-CLS, a similar instrument on the Cassini mission to Saturn. On the x-axis, we have time. On the y-axis, we have the energy bins. The counts for each bin at each time step are indicated by the colors on the right. Cassini encountered two types of transitions between magnetic field regions. The first is the more prominent bow shock, and the second is the more subtle magnetopause transition. We can see that the dimensionality of the time series is the number of bins used. What are the advantages of a responsive instrument? In the case of Europa, the magnetic environment regions themselves are poorly understood. These methods can help pinpoint boundaries. Also, we can capture a greater number of electromagnetic phenomena of scientific interest at the best range of observing energies. Here are two examples of electromagnetic phenomena as seen in CAP's ELS data. On the left, we have the discovery of high-energy electrons near Enceladus. These were used as evidence of electromagnetic coupling between Saturn and Enceladus. On the right, we have negative ions near Titan. Both of these were extremely important scientific discoveries. Why is this problem so hard? The biggest constraint is a severe restriction on the computational resources on the spacecraft. This restricts us to simple methods. The boundaries between magnetic regions are not sharp. This is especially evident in the magnetopause transitions in the CAP-CLS data. Within a region too, there are many local variations. Some of these are caused due to actual electromagnetic phenomena that we do not want to misdetect as a transition. Finally, the variation in the spacecraft trajectory across orbits leads to different angles of interaction with the boundaries. This problem can be approached in multiple ways. However, with an iron simplicity, we selected the following algorithms. The first is a baseline, which treats the counts obtained at each time step as a vector. It then computes the L2 difference between vectors at adjacent time steps. Hidden Markov models, both non-Bayesian and Bayesian variants, can segment the time series into multiple hidden states. Then, transitions between hidden states map to transitions between magnetic field regions. Impulsive is an algorithm that tries to estimate the probability density ratio between the set of current observations and the set of previous observations. Once this probability density ratio is estimated via a kernel model, a change point score can be computed as the divergence between these two distributions. Hotsax and matrix profile are two algorithms that try to find discords, the time series subsequences which have the highest nearest neighbor distance. The idea here is that subsequences that overlap with the transitions are rare and hence would have high nearest neighbor distance. Hotsax is an older algorithm that just finds the discords. while the matrix profile computes the nearest neighbor distance for all time series subsequences via some clever algorithmic tricks. The original matrix profile algorithm was developed for unidimensional time series. Multidimensional variants have been developed, but these mask discords that span only over a subset of dimensions. We instead propose an anomaly sensitive variant that uses the individual matrix profiles over each independent dimension and then just sums over them. We can identify discords that span only a subset of dimensions by restricting to the largest matrix profiles for each time step. Here are the multidimensional matrix profile scores on the previously shown CAPS ELS observation of the negative ion population near Titan. We see here that the scores peak exactly near when the negative ions are first detected. For each of the algorithms, we chose parameters via a validation set consisting of data from 2004. We then report performance on data from 2005 to 2012. We see that consistently, the Bauscher crossings are detected much better than the magnetopause crossings. Further, the matrix profile is the best at detecting the Bauscher crossings. However, across both categories, the non-Bayesian HMM is relatively better. The key contributions of our work are to propose an extension of the matrix profile for discord detection in multivariate data, and we have defined a new challenging time series analysis task that simple methods can still not succeed at. In the future, we want to investigate supervised learning methods. This would involve using data from the first few flybys of Europa, have a human annotate them, and then using machine learning algorithms over these labeled time series. We also want to investigate online change detection methods, which would handle observations in a streaming fashion instead of looking at 6-hour-long observations like we have here. We also want to benchmark runtimes of these algorithms in a flight system setting. This would allow us to capture the impact of running these algorithms on the spacecraft's resources. Finally, for a mission like Europa Clipper, which will be exposed to huge amount of radiation, it is important to assess how sensitive these algorithms are to bit flips caused in memory by radiation. That brings us to the end of this talk. We would like to thank everybody who has helped us and continues to help us for their guidance and their time. Finally, if you have any questions, please feel free to contact me. Thank you.